Hi, we're back. Thank you all for tuning into the second episode. I guess we are calling it Pushing Voxels Forward, considering that's what the title of the first episode was called, and it had a thumbnail and everything made, so it's official now. I just wanted to take a quick moment to thank you all for leaving feedback and likes and all that stuff. It was pretty cool to see. But enough of that. I've been working on the C project here, and I'll just quickly show you what I have. So we have our entry file, now much a better structure. Kind of the format that we're going with here is to create, I have a debug scene here, and then we're going to have a voxel scene, and the idea is that all of the OpenGL initialization code is going to go in this core file here, and then all of the specific code like the camera, setting up the 3D environment, all that stuff will be in these scenes. And this debug scene is just to render a cube. I'll show you that real quick. I actually copied most of the code that I have from the camera class in my C# project over to this, which is just a really simple smooth camera. I actually only have 4 faces on this cube here because I kind of got lazy and just didn't do the last 2. Also, I hope the audio sounds a bit better. The last episode was kind of noisy because I had my AC on, and I decided that that's not a good idea. So hopefully it's a little bit better this time. So looking at this core file here, we have, like I said, the OpenGL initialization code. And we are using modern OpenGL, by the way, none of the immediate mode stuff. And then we have this run function, and it's pretty standard. I copied a lot of this from my 2D game project, which is in C using SFML, which I probably copied from some online article. But it's the idea where you update a specific with a specific time step and then render as often as you can, which is really simple. I don't do the interpolation though on the rendering just because I don't like having to program it that way. So I just handle the camera updating in the update loop, even though there's really no point to doing that if I'm not going to interpolate the camera stuff, but it's fine. I mean, it works for the whole purpose of it. Here's what the camera stuff looks like, just in case you were curious. By all means, it's not optimized, hence the order of the variables here. And then here's the code. I'm using a library called CGLM, I think it's called. We should be able to see it if you look here. Yeah, CGLM, you can get it off GitHub. It's basically a C port of the core functionality of GLM. I don't know what the error is there for, but really simple stuff. WASD movement. Here's the smooth stuff. Here's the rotation. And then it's just real smooth stuff. It's just every frame, it just multiplies the velocity by a specified smoothness, which in this case is 0.85, which seems to be really good. And then just the rest of the standard stuff here. So one of the things that I didn't really make clear in the last video was what our ultimate goal is. It's basically to render huge isosurfaces or scenes composed of voxels in real time, primarily using the CPU if we can get it to be real time enough in the CPU. Obviously, we're probably going to have to do a lot of the stuff on the GPU, like generating noise and that sort of thing, because the CPU just honestly isn't fast enough. But for the mesh extraction, I think that we can get it on the CPU, and that's the ultimate goal. And by huge, I'm talking about like planetary size, just in insanely quick times. So here's like something real simple. It's just a sphere with some offset noise. And I did jump over to the C# project real quick because I actually wanted to show off an issue that I've been trying to figure out how I want to solve. So here we have some pretty nice detail. It's kind of just like that one noise scene that I showed you. It's got really nice detail up front, and then we can zoom out. This time it's just applied to a sphere. But as I get further away and I rotate the camera, I'm not sure if you can really clearly see it on video, but even the smallest movements seem very jagged. It's not really smooth, and the reason for that is just because of how we handle the camera. basically the floating points are just running out of precision, and we can fix that kind of using doubles, but I would much rather not. So I think that what I'm going to be doing, of course, is keeping the camera at the origin so we don't have to worry about the rotation, like the rotation matrices losing precision. I guess the rotation would lose precision, but the camera's target or look at would lose precision, and then that's where you face those kinds of issues. And then just moving and scaling everything else. So we're going to look towards a chunked based system. And honestly, I think that we're probably going to go with the dual marching cubes based idea that I had, just because the quality is better, and I think it's a little bit easier to work with in a chunked environment. So a lot of you at this point are probably thinking, hey, people can already extract planets in real time. There have been several projects on it, like No Man's Sky, for instance. The only thing that I don't like about that approach is they usually will use a height map and then map it to a sphere, and then you lose a lot of information that way. Like, this scene honestly probably could get away with a height map pretty easily, but as soon as we get up to here, we're going to be losing certainly some of the information that we have by only having 2 dimensions. So that's why I would really prefer to have a 3D extraction at a planetary scale, just because it would just be so much cooler. That was kind of supposed to be a joke, but it didn't really come off. I'm really close to the mic right now. Hey. I'd like to show you all an algorithm that came out almost 10 years ago now, called SnapMC. The paper is titled Quality Isosurface Mesh Generation Using an Extended Marching Cubes Lookup Table. You can see it right there. And it's honestly a really cool algorithm. It's basically the same thing as marching cubes, but instead of using just minus and positive or inside and outside edge or vertex markings, it uses negative equals and positive, or inside, on, and outside the surface. And so what this allows you to do is, given a certain threshold that you can control, if a vertex is close enough to the surface, or grid vertex I should say, is close enough to the surface, you snap that grid vertex to it, and then the extended lookup table will allow you to generate the same mesh, but it eliminates the sliver triangles, as you can see right here. It's clearly marching cube style mesh, but it's just got these slivers eliminated. And the cool thing is, I think this came out of Ohio State University, and the authors of this paper actually published an implementation for generating the table on their website. And for some reason I had a hard time getting it at one point or another, but I finally managed to get it. I dumped the tables, and then I was able to fix it so it conformed with triangle orientation as well. I have it here, and if you follow my Twitter, you can actually find where I pasted this table on Pastebin. So if you wanted to go ahead and implement it yourself, you can definitely do so. But I think as our kind of just breaking in the C project, we're going to go ahead and just implement uniform SnapMC, and then we'll probably try to use that with the ultimate mesh extraction, because if we can eliminate the sliver triangles at minimal cost, that's going to be awesome. By the way, real quickly, here's what the results of the dual marching cubes based algorithm can look like. I think this is without a sub-resolution and Laplacian smoothing applied to it. And then I can go here, and then it's kind of the same thing. As you can see, incredibly high levels of detail, and then this was extracted in about 3 seconds. It still has that timing at the top. And then here is where you can kind of see those artifacts that I was talking about, especially right here. Like, a lot of those triangles don't really add a whole lot of detail, but this just kind of gives you an idea of how massive the scene is, because that wireframe is a solid white right there. And this was extracted in about 4 seconds. Again, all totally unoptimized, but I think with the right optimizations we can get this working in real time. So there's one final thing that I haven't really touched on yet, and that's how we're going to be handling sharp features. And to tell you the truth, I'm not entirely sure. Right now we're in the diamond marching cubes with the tetrahedral stuff back at the C# project again, where we have a cube that just happens to be aligned in the right way where it does properly render it. The negative equals positive marching cubes extraction will help with this a little bit, especially if we're going to be able to move the grid vertices. There are papers out there that deal with sharp features with marching cubes, but honestly I'm more concerned about the speed and kind of overall triangle quality than I am about the sharp features, at least for now, because I think with post-processing there might be a way to actually get sharp features working. But again, our whole ultimate goal is to kind of extract planets and terrain in real time. Alright guys, well I think that's going to do it for this episode. Let me know what you think about the format of this, if you like how I'm kind of just recapping things, or if you'd prefer that I actually sit down and then I show you guys how I'm working through problems. It doesn't really apply right now because there haven't really been many problems to work through. It's been just me Googling OpenGL stuff and then figuring out how it all works compared to DirectX, just stuff like that. But you know, do you prefer the shorter episodes or the longer episodes? Just leave feedback and I will do my best to satisfy everybody. But until next time, again, be sure to check out voxelspace.net if you haven't already, and thank you all for watching. I'll see you next time.
Dual Conjuring.